Hello. This video will cover atoms, ions, and isotopes. So the development of the atomic theory has been going on for over 7,000 years. But not a lot happened for the first 6,800 or so years. It's only been over the last 235 years that there have been major developments in the atomic theory. We're going to focus on just a couple of those fundamental laws. In 1789, Lavoisier came up with the law of conservation of mass. It essentially says that mass can't be created or destroyed. So if we have 2 grams of hydrogen reacting with 16 grams of oxygen, we would end up forming 18 grams of water. Law of conservation of mass. In 1794, Proust came up with the law of definite proportions. And that states that all samples of a pure compound contain the same elements in the same proportions by mass. So water will always be 11.2% hydrogen and 88.8% oxygen. Marsh gas or methane would always be 74.9% carbon and 25.1% hydrogen. Dalton's law of multiple proportions states that when 2 elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in small whole number ratios. So what does that mean? Water and hydrogen peroxide both contain hydrogen and oxygen. If we have a fixed mass of hydrogen for either of these 2 compounds, the masses of the oxygen in each of those compounds will be in simple whole number ratios. Now, Dalton's law atomic theory has several different statements. The first statement essentially says that matter is made up of atoms, and atoms are really small. The second statement says that atoms of the same element are all the same. So atoms of the element hydrogen are all the same, and atoms of the element oxygen are all the same. The third statement states that if atoms of one element are different from atoms of another element. So atoms of the element hydrogen would be different than atoms of the element oxygen. And the fourth statement deals with compounds. Compounds are 2 or more different elements that are combined together in some type of small whole number ratio. And this provides a microscopic explanation for everyday observations. So if we have a container here that has copper and oxygen in it, and the copper and oxygen react to form copper oxide, we'd see that the atoms are neither created nor destroyed during that chemical change, but instead they're just rearranged to produce substances that are different than what we had to start with. Now, when we look at an atom is made up of several different types of subatomic particles. The first one to be discovered was the electron. So J.J. Thomson had cathode ray tubes. He exposed a metal sample to high voltage, and he produced a visible beam, a cathode ray. But that cathode ray wasn't light because it could move matter. So instead, it must be made of some unknown particle that's smaller than an atom. Now, that beam always flowed from negative to positive. And when it was subjected to a magnet, it was always pulled towards the positive side of that magnet. They concluded that the particle must have a negative charge, and the electron was discovered. J.J. Thomson also came up with the charge to mass ratio of an electron as being 1.759 times 10 to the 11th coulombs of charge per kilogram of mass. Now, J.J. Thomson came up with the charge to mass ratio, but he didn't know whether those electrons were large with large charges or small with small charges. So Robert Millikan did an oil drop experiment where he charged those oil droplets and then exposed them to a voltage until the oil drops stopped dropping. And he determined that the charge that causes those oil drops to stop moving was always a multiple of 1.6 times 10 to the minus 19 coulombs. And from that information, he determined that the mass of an electron is 9.107 times 10 to the minus 31 kilograms. Okay, so the next question was, atoms are made of electrons, but where are the electrons in those atoms? So early on in the beginning of the 1900s, Nagaku said that the atom was arranged something like a Saturn model, where we have the positively charged matter in the center and the electrons are kind of a ring around that positively charged matter. In 1904, Rutherford came up with the plum pudding model, which essentially said that we have this positively charged matter and the electrons are embedded within that positive charge. So then they started experimenting. So Rutherford and some other scientists shot alpha particles into a thin gold foil. A small number of those particles were deflected almost straight back. And Rutherford said, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Now, they didn't know what alpha particles were. Okay, we know now that alpha particles are made out of 2 protons and 2 neutrons. And they generated those alpha particles. They passed them through the gold foil, and there was a detector that showed where those alpha particles went. So either the plum pudding model or the Saturn model was, if that was correct, the alpha particles would go straight through, but they didn't. Some of the particles are deflected, indicating that there is a presence of a positive charge in the atom. And a few particles bounced back, indicating that that positive charge is very dense in that atom. So if we look a little bit closer at the gold foil experiment, we have our piece of gold foil, very thin gold foil here. We have our alpha particles passing through. Some of the alpha particles went straight through, which is what they expected. Some of the alpha particles were deflected a little bit, and some of the alpha particles actually bounced back towards the original source. Now, if we look at a more blown up picture, each of these is a gold atom. This little center here is the nucleus of that gold atom. Now, some of the alpha particles went straight through the gold foil, which is what they expected. Some of those alpha particles were deflected just a little bit, and some of those alpha particles were deflected all the way back towards the original source. The conclusion they came up with was the atom must contain a very small, very dense, positive particle, the nucleus. Now, when we talk about isotopes and the mass quandary, after more work, Rutherford determined the source of the positive charges in the nucleus was a proton, and that the proton is 1,800 times heavier than an electron. And when we look at a neutral carbon atom, it contains 6 electrons and 6 protons. But the mass of that carbon atom is about equal to 12 protons. So there must be some neutral particles that add mass without charge in an atom. So during the early 1900s, scientists isolated elements with masses differing from what they expected. And then Soddy proposed that elements could have different types of atoms, which are called isotopes. And these isotopes were formed through the presence of neutral particles called neutrons. And these neutrons have mass, but they have no charge. And the neutrons were first isolated by Chadwick in 1932. So if we were to look at the nucleus of an atom, we've got these positive protons And then we've got these neutral neutrons that add mass but no charge. So here are two models of hydrogen atoms. Here we've got what's called hydrogen 1. It has one proton in its nucleus, and it has one electron outside its nucleus. There's another form of hydrogen called hydrogen 2. It's sometimes referred to as deuterium. It also has one proton in its nucleus and one electron outside its nucleus, but it also has a neutron in its nucleus. That's where the 2 comes from in its name. One proton plus one neutron equals 2 particles in the nucleus. And the mass number is equal to the protons plus the neutrons. Now, when we look at an atom is small, and the nucleus is even smaller. The nucleus is about 100,000 times smaller than the whole atom. So the particles inside an atom have to be even smaller than that. So if we look at a very basic diagram, the diameter of a typical atom is about 10 to the minus 10 meters, which is super small. But the nucleus is 10 to the minus 15 meters in diameter, which is about 100,000 times smaller. And the subatomic particles, the protons and the neutrons and the electrons, they have to be smaller still. So if we look here, we've got properties of the atomic particles. We really need to know the information that's in the red boxes. So we need to know that electrons are found outside the nucleus. Their unit charge is -1. And their mass is almost 0. Protons are found inside the nucleus. Their unit charge is +1, and their mass is roughly 1 AMU, atomic mass unit. And neutrons are also found in the nucleus. They have a unit charge of 0, and their mass is almost the same as the mass of a proton. Now let's look at chemical symbols. Okay, they can contain 1 or 2 letters, and they're abbreviations for the element names. Now, sometimes it's easy to determine what the symbol for an element is. Oftentimes it's not, because sometimes the root of that element name isn't from English. So if we look here at a list of some common elements, we have carbon. The symbol would be a capital C. We've got calcium. The symbol can't be a capital C because that's carbon. So it's a capital C and a lowercase a. If we were to look at cobalt, that couldn't be C for its symbol. So it's capital C, lowercase o. And if we were to look at copper, which can't be C, copper is actually Cu, which comes from cuprum, which is Latin for copper. Now, when we look on the periodic table, there are 3 things that are typically found in each box on the periodic table. The symbol, the atomic number, which is the whole number on the periodic table, and the atomic weight, which is the decimal number. And we're going to be using that information to answer various questions. So we want to talk about what's called the isotopes symbolism. So we're going to use an X to stand for our element's symbol, Z to stand for the atomic number, and the atomic number defines the element, and it's equal to the number of protons that are found in the nucleus of that atom. A stands for the mass number, and the mass number is equal to the number of nucleons, protons or neutrons, that are found in the nucleus. And C stands for the charge on that atom, which is the sum of the protons and the electrons in that particular particle. For atoms, since the number of protons equals the number of neutrons, that value would be 0. So when we look at the element symbol here, okay, this would be the symbol off the periodic table. This would be the atomic number, which equals the number of protons. And when atoms are neutral, it also equals the number of electrons. We've got A here, which is our mass number, that equals the number of protons plus the number of neutrons. And we've got C here, which is the atomic charge. How do we determine the number of neutrons in an atom? If the mass number is the number of protons and the number of neutrons, and the atomic number is the number of protons, if we take the mass number and subtract the atomic number, that'll give us the number of neutrons. Now, when we talk about an ion is an electrically charged particle obtained from an atom or a chemically bonded group of atoms by adding or removing electrons. So the only thing that changes when an atom becomes an ion is the number of electrons in that particular particle. When an atom loses an electron, it becomes positively charged, and we call that a cation. When an atom gains an electron, it becomes negatively charged, and we call that an anion. And then we have a cute little cartoon here. I'm hit. I've lost an electron. Are you sure? I'm positive. Okay, so we have this table here, and we want to complete all the information. So here we're given the element carbon. This is the mass number here. So this equals the number of protons plus the number of neutrons. We're either told it's an atom, which means it's neutral, or we're told it's an ion, which it has a charge. Now, the number of protons comes from the atomic number, which we get off the periodic table. And that's where these numbers come from. If atoms are neutral, the number of protons equals the number of electrons. So this column would be the same as this column. If it's a negatively charged ion, it's gained electrons. And if it's a positively charged ion, it's lost electrons. Now, to figure out the number of neutrons, we would take the mass number, which is the number of protons plus neutrons, and subtract the atomic number, which is the number of protons, and that'll leave us with the number of neutrons. So you want to stop this video for a second, see if you can fill in this table, and then we'll look at the answers. So when we look at carbon, the atomic number is 6, which means we've got 6 protons. It's an atom, so it's neutral. It has 6 electrons. And we take the mass number, which is 14, subtract the number of protons, and that gives us the number of neutrons, which is 8. If we have sodium 23 that has a +1 charge, we look up sodium on the periodic table. Its atomic number is 11, so it's got 11 protons. But it's not neutral. It's got a +1 charge. That means it lost an electron. So now it's only got 10. To figure out the number of neutrons, we would take the mass number, 23, subtract the atomic number, 11, and that would give us 12. Okay, the next one, we've got sulfur 32, and it's got a charge of -1. So we look up sulfur on the periodic table. Its atomic number is 16, so it's got 16 protons. If it were neutral, it would have 16 electrons, but it's got a -2 charge. That means it gained 2 electrons, so now it's got 18 electrons. To figure out the number of neutrons, we would take the mass number, 32, and subtract the atomic number, 16, and that would give us the number of neutrons. Now, the next one's a little bit different because we're not told what the element is, but we're told the number of protons. The number of protons is 13. That means the atomic number is 13. If we look up the element on the periodic table with an atomic number of 13, we're looking at aluminum. Now, it doesn't tell us it has a charge, so the number of protons equals the number of electrons. And if we've got 14 neutrons and 13 protons, the mass number is 27. If we look at the next one, okay, we're told it's zinc. We've got 30 protons. It's got a +2 charge, so it lost 2 electrons. And if I take the protons plus the neutrons, that will give me my mass number of 65. If I've got oxygen 18 and it's an atom, and I look oxygen up on the periodic table, the atomic number is 8. So that means it's got 8 protons. It's neutral because it's an atom, so it's got 8 electrons. And if I take the mass number and subtract the number of protons, that'll tell me the number of neutrons, which is 10. Now, not all isotopes are equal. Okay, some atoms only have one isotope, while other atoms have many isotopes. And not all isotopes are radioactive either. So if I were to look at hydrogen, hydrogen has 3 isotopes: hydrogen 1, hydrogen 2, and hydrogen 3. They differ in their number of neutrons. I have no neutrons here, 1 neutron here, 2 neutrons here. And if I look, their percent abundance isn't the same. Almost every form of hydrogen is hydrogen 1. Only a very small percentage is hydrogen 2, and almost none of them are hydrogen 3. And hydrogen 3 is radioactive because it's so unstable. Fluorine only has 1 common isotope. Nickel has 5 common isotopes. Their atomic numbers are the same. Their mass numbers are differing because their number of neutrons are differing. And then carbon has 3 isotopes. Carbon 12 is the most abundant by far, 98%, almost 99%. Carbon 13 is a little bit, and carbon 14 only has trace amounts because, again, it's a radioactive isotope. It's not stable at all. Now, when I look on the periodic table, the atomic mass is not a whole number, and it doesn't match any of the individual isotopes. We want to know why. So let's look at carbon as our example. There are 3 isotopes of carbon, carbon 12, carbon 13, and carbon 14. If we look at their masses, none of these numbers match the information on the periodic table. But we can do a calculation because the atomic mass on the periodic table is the weighted average of all of the isotopes of that element. How do we calculate that? To calculate the average mass, we would take the sum of all of the isotopes. We take the mass of each isotope and multiply it by its abundance, and then add them all together. So if we look at carbon and we want to find out the weighted average mass, we would take the fraction abundance times the mass in AMUs. And then we take carbon 13, we take the fraction abundance, multiply it by the mass in AMUs, and then we wouldn't even include carbon 14 because it's in such a small amount, it's not even registering as a fraction abundance. So we take the fraction abundance, we'd multiply it by the isotomic mass, we'd add those up for all of the isotopes, and that would give us our weighted average in AMUs. This number matches up with what's on the periodic table. So let's look at another example. Boron has 2 isotopes. You're given the isotopic mass in terms of AMUs. You're given the abundance. You want to calculate the weighted average. So stop this video and try and do that calculation, and then we'll look at your answer. So we've got 10.013 times 0.1991, and we're going to add that to 11.009 times 0.8009. And that gives us 10.811 AMUs. And this is the number on the periodic table because the number on the periodic table is a weighted average of all the isotopes of that element. Now, let's look at a different kind of question. It says naturally occurring copper consists of copper 63, and it gives us the AMU for the mass, and copper 65. It gives us the mass in AMUs. And this time it tells us what the weighted average is. We want to find out what the abundance of each of those isotopes are. So we're going to work the problem backwards. This time we know what the total is. We don't know what the percents are. But if we say that copper 63 is X, copper 65 has to be 1 minus X because they're the only 2 isotopes that exist for copper. So then we just have to do some math. We'll distribute into our parentheses. We're going to isolate our X variable. We're going to solve for X, and that's going to give us our natural abundance for each isotope. So copper 63 is 69.15%, whereas copper 65 is 30.85%. Now, where do they get this information from? They use what's called a mass spectrometer. So the sample would enter here. It would become a vapor. It would become ions that are accelerated, and then those accelerated ions would pass through a magnet. The particles that are heavier are going to be bent more, deflected more. The particles that are lighter would be deflected less. And then we've got a detector here that would give us our percents, where those numbers come from for the previous couple problems.